Good afternoon. Okay. So, last time we talked about pyrrole synthesis 1, this time pyrrole synthesis 2. Okay, means what it means, actually there are so many methods for assembling the pyrrole unit structures, okay, and it can be subdivided into several classes, and there could be, I mean, if you go to the website, go to the Google, you will find at least there are 60 different methods listed in the Googles. There is a site called Organic Portal, you will find. So, it is not possible to obviously to talk about all those methods, but I have picked up some of the methods. In the last class we talked about largely Barton, Judd, then Van Leeuwenhoek, then Piloty and Robinson. Okay. Piloty, Robinson and then Jana is one. Okay. Today what I will do, I will just go through very quickly the conventional ones. There are 3 conventional ones, and then I will talk about there is a method developed by Chiba, and then methods based on alkynes, and then method based on ring contraction and ring expansions. So, these are the few things we will be talking about today, and then if you see, if you try to master the methods on pyrrole synthesis, because it is a very useful nucleus, you will find in by bispyrrole, tripyrrole, then so many natural products, then obviously many of you know porphyrin itself is a real big class. So, if you want to make a porphyrin modified compounds or porphyrin based compounds, then you have to know about the pyrrole chemistry. Okay. So, what do we do today? Just basically we classify them into terms of like the components. If you recall, the last time we talked about most of the pyrrole synthesis are based on 2 categories, 4+1 and 3+2. Okay. So, when you talk about the 4+1, then among them the most popular ones are Pol-Nor synthesis, that is the first one. Then these what is that? Next one is Hunt synthesis, that is the most, and then Nor synthesis. These are the 3 conventional ones. But among the 3, then Pol-Nor is very powerful. Even today, if you come across a pyrrole nucleus, the very first thing what you should think about is to think about the Pol-Nor, because that is more readily as most reliable, and primarily this is most popular because of what? Because of ready formation of or very I say facile formation of 5-membered ring system. See, all of us know that cyclization is among the cyclizations 5-membered formation is very fast. I mean officially, I mean 3, 4 all these people is arguable, but in practicality the 5-membered ring formation is much faster than many other ring systems. So, that facile formation of 5-member actually makes this Pol-Nor more popular than other. Okay. And I will just give you one example that I mean just to tell you that how powerful it is. So, that means today we talk about there are 3 categories. The first category we talk about the conventional ones, and then second category we will talk about this. This is basically this is called Chiba's method, and third one starting with alkyne precursors. Then fourth category could be ring expansion, and then obviously this other one could be the ring construction strategies. Okay. Now, when you talk about the Pol-Nor, I think many of you know it requires basically Pol-Nor requires 1,4 diketo compounds, but there are examples where you will find you do not need to have this 1,4 diketo compounds, but the corresponding precursor is good enough. If you look at the one I have written here, it is basically a tetrahydrofuran derivative, right, and then you react with ethanol amine and using a solvent acetic acid. So, what we expect here just a pyrrole. So, that means the product here is just a pyrrole with ethanol side chains on nitrogen. Mechanistically this is equivalent to what is, this is equivalent to. So, again it is just a succinaldehyde, is not it? Just if you hydrolyze this, it will give rise to succinaldehyde, and then now the questions what we had been talking about, that between amine and alcohol, all of us know amine is more nucleophilic. So, it will undergo condensation, and then Schiff's formation is also very fast. So, once this condensation takes place, then there are all possibilities. Of course, the 5-membered ring system would be formed first, and this is the one that is. Now, just we will have a little more complex example to illustrate this particular one, how so powerful it is. Let us say if you begin with a multi-substituted, let us say multi-substituted ketone, and in this case the substituents could be benzene ring, then then one more ketone here, then NH, and then see, I mean you have all kind. This reaction has been particular, this reaction. So, what you see here, you have an isopropyl side chain, then phenyl side chain here, fluorophenyl side chains, then this aniline side chain, and you do not have to do much. You do not have to do much. Just take an amine, and then of course, in this case this is a protected amine here with acetal protection, this one, and just simply take acetic acid and heat it. So, what do you expect? Let us say if you did not know, polymer synthesis, now we know polymer synthesis. So, it will give or it will provide a pyrrole nucleus, but if you did not know where do you start from, basically you have to look at the different functional groups. You have 2 ketones, you have 1,4-diketones, then you have 1,3-diketones also, but okay. But when you heat it, actually what you get is again a pyrrole. So, it is now a tetra-substituted pyrrole. So, now what you get is a tetra-substituted pyrrole, and I think something is wrong somewhere. 1, 2, 3, 4. Okay. So, this should be a fluorine hub here, right, and then this should be phenyl, and this is CONH, and this is again phenyl, and then what? Then you have this nitrogen, this one Me, OMe and OMe. So, okay. So, what do you see? That means out of the 3 carbonyl groups, one can very quickly guess that amide carbonyl is less reactive, less electrophilic in nature. So, that means 1, 2, 3, 4, these 4 I mean this 4 carbon unit would condense with this ammonia to give this pyrrole unit, right. And what is specialty about this reaction? Because it can assemble all the 4 different substituents in right manner, and actually tetra-substituted pyrrole formation is difficult. If you try to carry out in stepwise manner, first one or two, first and second can be introduced very easily, third when you try to introduce that would involve steric effect. So, then fourth one even more steric effect. So, that means stepwise processes are not that welcome in this sort of reactions. But what next? Actually if you just change the side chain, with a 7 carbon unit, 1, 2, 3, 4, 5, 6, 7, I think 1, 2, 3, 4, 5, 6, 7 carbon unit here, and then if you have OH groups here, there are two OH groups. Basically this is nothing but it is the substitute for the amine, then the resulting product, that the resulting product would be, if you take this amine and the resulting product would be something is one of the highest selling drug in the world. This is called Lipitor. It is marketed by Pfizer, and it actually is used for the treatment of cardiovascular diseases, and actually it lowers down the cholesterol level in the blood. Okay, it is a very high selling drug, and so you can see here, this is a carboxylic acid, that is a very useful one. Okay. And so likewise, I mean many of the recent pyrrole synthesis would depend on this sort of Paul-Knorr synthesis. The second one of course Hunt synthesis. Hunt synthesis, I think many of you, I guess you know, right. What are the how do I remember, how do we remember Hunt synthesis? Hunt synthesis basically in heterocyclic chemistry try to remember on the basis of the starting material. That actually makes you learn heterocyclic chemistry little easier. Okay. Because like say in the previous example 1 4. So, then 4 plus 1 unit, in this case 3 plus 2. Now, depending on the situation you can remember which one is 3, which one is 4. 3 means normally what do we talk about? We talk about this enamine, right. So, we talk about this enamine, right, and then other thing is what else you need? 2 carbon unit. So, it has to, that means this nitrogen side you will have to have a right. So, you have to have chlorine in one case and the alpha chloroacetone kind of things, alpha chloroacetone. Okay. And mechanistically I think all of us know how do we carry out this reaction, just simply mix them and heat it, nothing else. So, all of us know, and there could be two mechanisms, there could be two different mechanisms. One can involve this displacement of the chlorine through the enamine here and then condensation, or the vice versa you can do also without any problem. I mean, so, but in fact this is more likely that enamine as undergoing C bond formation to give the corresponding and then as usual the ketone amine condensation would give rise to the product which is now what you will see is 2,3 disubstituted. So, this is a standard protocol of the hands. Okay. And then how do we make this enamine ester? Enamine ester also I told you before it is pretty easy to make. Simply take this corresponding keto compound and just treat with ammonia, that is it. And in this case you can do just aqueous ammonia is sufficiently good enough. Aqueous ammonia that would forms the imine first and then isomerizes to enamines. Okay. And this third category I think all of you know, this is called Knorr synthesis. This is not that very popular though, only in certain special cases they are used. It is used. This is again, so you have to, as I said before, you have to base your memory, or rather you have to memorize this thing on the basis of the starting material. What is the starting material? How do you remember? What is the starting material? How do you remember? Knorr synthesis. So, again it is a category, it belongs to 3 plus 2. So, that means you have to know the 3 plus component, 3 component, 3 atom component and the 4 atom 2 atom component. Okay. So, this is how one can remember. This is basically amino ketone, alpha amino ketone, that is what you have to remember. 1,4-diketone, then the next one was enamine, and the third one, that is in Knorr synthesis, would require alpha amino ketone. So, that is it. Once you have these, then this amine would require a carbonyl, and then the other part would require an active methylene compound. So, somewhat like a beta keto ester kind of thing, and then you have I mean for different purpose you have different substituent, and if you just again just simply heat it and reflux. So, what you will find? You will find through the amine ketone condensation. So, you will get this formation of without much problem, but without much problem here, but then it is not very popular. Who can tell me why? This is not very popular. It is not widely used like Pol-Nor synthesis. What could be the reason? Dimerization amino ketone, right. So, basically that means first of all this amino ketone formation is little difficult. So, we are actually the number of methods available for formation of this alpha amino ketones, and many of you know this amine and ketones when mixed together they are automatically forms imine to some extent. Once the imine is formed, it can undergo isomerization, tautomerizations, all different kinds of things. So, any case, but all of you know I guess how to make this amine. The standard way is to basically you take the corresponding beta keto ester, right, beta keto ester, and then you treat with nitrous acid. So, if you treat with nitrous acid, so what you will be getting? You will be getting the ketone here and is then oxime, So, just like your nitration of phenol, you see a nitroso compound, but nitroso compound in this case isomerized to oxime, and then this oxime is reduced with zinc acetic acid. So, this is the standard protocol. Okay. So, what next? So, that means you see here in Hans synthesis you have basically a component with nitrogen with 2 carbon, CCN, and in Nor synthesis also CCN system. There is a very recent method which has been developed by a scientist named Chiba, and he developed a new synthesis in 2008. What he did, his starting materials are very simple. He used this something like this. Sorry. So, what is that? As 2-azido acrylate. So, this is the starting material. Then what he used, and other thing that he used is again a 2 carbon unit. So, it is an ethyl ester and ethyl ester, carbonyl and CH3. So, here you see that means basically again 1, 2, 3 carbon, nitrogen. So, azide group actually provides only 1 nitrogen, and at the end of the reaction what you get is now is a tetrasubstituted pyrrole, and this is phenyl, then ester here, and this is then in this case it is ester. So, I mean very similar to what? If you can just basically compare, this is when you proceed forward, you have to have something in back of your mind. It resembles something. I mean, you have to have a foundation. Based on the foundation, you grow your knowledge, right? So, in previous examples, we have seen 3 units. So, 3 enamine. So, it is very similar to enamine. Enamine, what does it have? Carbon and a nitrogen. So, carbon and a nitrogen, and the azide actually provides a single nitrogen, and the other 2 nitrogens are lost as nitrogen molecule. Okay. And of course, it is not that easy to discover a reaction. I mean, it took long time, and it works pretty well with a catalyst. In this case, the catalyst is copper 2 bis triflimide. Copper 2 bis triflimide. I guess I do not have to explain the structure. Copper 2 bis triflimide means N here and trifluoro sulfonyl trifluorosulfonyl. Okay. So, in this case that means it would be copper here one more, right, one more. So, basically structure would be trifluoro bis trifluorotriplyamide. Okay. So, so this is but the amount of catalyst is very little. So, normally it is 10 to 12%, and what else, and what is unique about this, it is the structure, sorry, it is the reaction condition, only 40 degree centigrade, only 40 degree centigrade. So, you get very high yield. In most cases the yields are very good. There are about I mean dozens of examples done. So, what is the mechanism? Mechanism actually I can write the mechanism, but you can also work out this mechanism. First of all, see, many of you know most of these transition metal like copper, iron, all these things, they form the complex with diketone compounds, 1,3-diketon compounds. So, in this case what has been done here, so it enol form, I should write here enol form here, okay, and then enol, and this is let us say ester. So, this then it forms again a sort of a copper complex here, and in the other case. So, what you will have, this is phenyl, then you have ester here. So, some sort of activation must be there, and the copper actually assist copper serves a dual role in this case. So, basically it activates this azide, and so it weakens this nitrogen bond here, and in this case it acts on the other side, actually it makes this 1,3-diketone more nucleophilic. So, as we are used to the electron bookkeeping, what we can see here, this is the oxygen minus, you can, if you consider oxygen minus. So, it goes via this electron movement as if it is undergoing kind of a Michael addition, You see here alpha beta unsaturated ester, right, and beta keto esters actually forms a nucleophilic center at the middle carbon, right. It undergoes Michael addition. So, this then it forms this anion here, but then anion now goes to expel this nitrogen. So, expel the nitrogen. So, what we eventually get? So, what we will have this is this ester part, and then this would be converted to the ketone, and then you have this phenyl group, and now you see here the carbon and nitrogen will be now carbon double bonded nitrogen, and then copper is attached to the nitrogen now. So, I mean you can have all kinds of mechanism, but to my mind nitrogen is now sort of a nucleophile again, nitrogen minus. So, this minus would now condense with the ketone here, and right. So, nitrogen ketone, and this is OH and the CH3 and then ester, eventually when you work it up, and then ester, and I think from now onward all of us should be able to write this structure, right. So, this loses water, and so what you will be getting, you will be getting this part unsaturated, and then what? Then obviously, these imines do not stay in the form here. So, in the presence of even weak acid, it will tautomerizes to I should say isomerizes to the corresponding this one. So, what? What is the conclusion? Conclusion How do you describe this? How do the whole see I have a full slide. Now we have to describe. How to describe that the Sivas procedure depends on the utilization of vinyl azides. This is important, number one. Other component is beta keto ester, it is a standard protocol in pyrrole chemistry, fine. Second important thing that is that you need a copper triplet, sorry triplimite, copper triplimite as the catalyst, and what else, and you require an ester group here, so that the initial Michael addition is feasible, fine. Then it and what is very important here, actually this is unique mechanistically, reason being you will not see many examples where you will have an imine nitrogen minus. Okay, that means what I am talking about, I am talking about a system like this. You will rarely see something like this. We see imine, we see base, everything, but here you do not see something like this one. So, this is being formed and very easily with 10 to 20% of this catalyst. Okay. And but then it has some limitation though, it has some limitation. What is the limitation? It requires electron withdrawing substituents like ester. Okay. But again the same person in the same year in a later paper, what he has done, he has just modified this procedure. He has modified this, and what he did, again vinyl azide, but in this case there is no electron withdrawing group, and this then again a beta keto ester here. Okay. Now what? How to okay. So, you have just basically again at around 40 degree centigrade in methanol, in the presence of a catalyst, he could produce the compound of this kind is a phenyl here. So, what is the again this is a 3 component 1, 2, 3 carbon nitrogen, in this case 2 atom component. So, principle is same, instead of the ester here you have a phenyl, but that did not work under the influence of the copper catalyst. So, you have to choose a right catalyst. So, what is the catalyst could be? Let us say when the many of you are the research scholars, right, when the reaction fails, what do you do? When a most obvious reaction fails, what do you do? You repeat first whether your hands are doing any mistake or not. Okay, you fail second times, then what do you do? Check the reagents. So, there are so many steps actually, the reagents. Okay. If it genuinely fails, then of course, then you have to think about the reaction mechanism and revise your the project or the scheme. Okay. So, let us say in the the paper says it does not work with the vinyl azides without electron withdrawing group. So, what can you do then? He could solve this problem in the same year. You just change the mechanism, because we are organic chemists, right. We know we have good knowledge of mechanism. You change the mechanism, and the mechanism, and we have a wide array of mechanism. At one end we have carbonium ion, other end you have carbon ion, in the middle you have anion radical, anion cation, anion radical, all these things, radical, carbene, nitrene, all these intermediates, right. And the other possible is the pericyclic reaction. So, we have a wide range of the reaction mechanism. In fact, when all of us know the Michael addition requires electron withdrawing group, but also at the same time we know radical does not require, even take polystyrene, put it in just empty bottle, it gets polymerized. Okay. So, ethylene polymerization, that means even polymerizations can be done under cationic condition, anionic condition, radical condition, all. So, once this is fails. So, actually what he used in this case, he used manganese triacetate. Why suddenly manganese triacetate? That is also important. How, of all so many acetates, so many things, why suddenly manganese triacetate? Because in the literature, if you go to the carbocyclic chemistry, you will find manganese triacetate is known to produce radical on the carbon between the ester and carbonyl of beta keto ester. That is no standard protocol. I mean, so manganese triacetate has been a very useful reagent, and one of the pioneer scientists is Barry B. Snyder. He has made lot of carbocycle. I mean, at the moment I cannot give you exact example, but I can roughly give you what he has done. Let us say if you have something like this, and then you have ester group here. I may not be exactly correct, but almost correct. Okay. If you have something like this, then you treat with manganese 3 acetate. So, you are likely to it is unlike simple aromatic chemistry, you can get this sort of compound. What is the mechanism? It looks like as if it is a Friedel-Crafts reaction, right, but it is not. Actually, it produces the radical here. Okay, so then of course, the benzene can trap this radical, etc., then rest of the things as usual. So, this is what he has modified though. I mean, you can sit down and do this mechanism, no problem. Just again let us say how he did. I have not picked up, but just basically he has used manganese to produce radical here, radical undergoes coordinations, then keeps on adding electron transfer there, here and there. Eventually, you get this loss of nitrogen like the previous one. Only thing that he has involved a reagent which can produce a carbon radical. Okay. What next? Again the same very similar compound. You just look at the compound. I just give you one more compound, and the same compound, let us say the one that we did previously. Let us take ethyl and the phenyl, and take acetyl acetone, then just heat it in toluene at 100 degree centigrade. You get 100% yield of a product, 100 yield of a product, and that is a pyrrole. What is it? No catalyst now. The product is this, and phenyl, and in this case you have here is an ester group here. So, what do you see? Carbon nitrogen, that means the azide vinyl azide gives the carbon nitrogen, then this beta ketone gives this again this only 2 carbon for the pyrrole, and it is strikingly different from the other 2. What is the difference? Other 2 also is very similar, but if you go back and see in the with copper bis trifluoride, the phenyl was at the 3 position, right, but here you get at the 2 position. That means, the reaction is somewhat complementary, and then reaction condition is very easy, just simply mixing them and hitting them in the solid toluene. Okay. So, what do you guess? So, what is the mechanism then? That means, we have changed the mechanism now from copper, which is a Michael addition, with manganese, which is a radical, and what else can you think of here, any mechanism? What is the mechanism you can think of?
So, the carbon ion generated in case of the
carbon ion generated in case of copper. Okay.
Generated in case of in this case by the 1,3 diketone compound.
What will be generated?
Carbon ion will be generated.
Carbon ion. Okay. See, I think in the 4th year also we talked about this thing. How to see, in the very first class we talked about the classification, etc. So, see, you are starting any for any organic purpose. When you even listen to the seminar, you try to concentrate on the reagent thing, try to recognize the reagent. Okay. What is the reagent in this case? heat, only heat, and when you come across heat, then you go to the straight away go to the pericyclic chapter, right. So, thermal reaction, most of the cases, all these thermal reactions are the pericyclic reactions. Okay. And other cases, so, and you get this neutral intermediates, nitrins and carbines. So, that means under thermal and photolytic conditions, what you come across only pericyclic reactions and for these nitrin, carbene, all these reactions, benzynes, those sort of reactions. Okay, thermal conditions also you can produce the benzynes. So, reactive intermediates or neutral reactive intermediates, not carbanion, not carbonium ions. Okay. So, I mean I think answer is now given, right. What is the answer? It ester here it produces nitrine. So, what next? If nitrine is produced, then it forms if nitrine is produced, it forms this is pH. So, it will be forming nitrogen double bond, this thing pH and this. So, what is it? Azirine, right. So, you get this this is pH, sorry. So, not aziridine. So, azirine nucleus you get, okay. Then what? Then you have beta diketone, right. Beta diketone, all of us know that in equilibrium it is enol, and you have now okay, this enol hydrogen can be transferred to nitrogen here, and then this goes to carbon double bond nitrogen. What is this reaction? Thermal condition, pericyclic reaction, very good, in reaction. So, in reaction, so once you have this in reaction, that means pH now and nitrogen, you have this ester here and then this one, okay. And what next? What is expected next here? See, many of you probably know aziridines, unlike epoxide, it has specialty. What is the specialty? Unlike epoxide, it has a special kind of a reaction, or rather between epoxide and aziridine. If you have proper activation, you will find aziridine opens up very quickly, ring opening takes place. Okay. That is what right, Vivek, in your lab do you do aziridine ring opening, right? You do not do that. Okay. You will see there are a lot of papers from Somen's lab, you will find aziridine ring opening and then recyclization with aromatic compounds. So, that is but in this case there is not much activation though, but probably under this thermal condition, normally this nitrogen is substituted by a sulfonyl group or electron withdrawing groups, so that you can make it open. And so, once this is done, then one can see that there is a thermal ring opening and then of course, you can in fact simultaneously do, but formally one can write this way though, double bond here carbonyl and this is a carbonyl here, and you can write nitrogen NH2 here, right. Then of course, 1 2 3 4 I think 5, any mistake somewhere maybe, I think we have made a mistake, yes, number of carbon is increased, sorry, rewrite please. So, that means this is ester here, double bond acetyl group, then you have acetyl group here and you have NH2. 1, 2, 3, 4, 5. Now, just a regular condensation of the amines and etcetera. So, you will be with OH methyl here and then double bond ketones, and this is a phenyl here and all these things. So, eventually you go to the product, So, you see here the means okay. So, what is the conclusion? The vinyl azide is a very versatile substrate. You can use it in different fashion, but one of the other reacting component has to be 1,3-diketo compounds. Okay. And vinyl azide does not have to have necessarily the electron withdrawing group. So, you can have all different kinds under cationic condition, anionic conditions, under radical conditions, anionic conditions and thermal conditions. Okay. And the same. Okay. So, that means what you see in all the 3 examples, if you see that 1,3-diketo compounds and it incorporates at least one electron withdrawing group, because one of the components is 1,3-diketo compounds. Okay. But again in 2011, very recently, what he has done, he has just a small modifications here. So, that you do not have to have, let us say if you take an R again a vinyl azide. Now, in principle it is a diketo compound. Now, let us say R1 and R2 here, you see very similar to the previous example. This is also beta keto acid now, but without the carboxylic acid it looks like just a simple ketone. So, result would be then this is a pyrrole with now plain alkyl groups now, without a ester group, and this, So, that means from the corresponding beta keto carboxylic acid very similar, but in this case because it is a carboxylic acid, eventually it is lost from the reaction, and in this case the mechanism is very similar to again a radical mechanism, but the catalyst here is manganese acetyl acetone, and the percentage of course is normally 10%, Okay. Fine. What next? I think when I talked about this, let us say there are other methods, maybe in very similar fashion. Let us say now if you have an azide and again ester, then double bond and something like this. Now, do the same thing very in the so now we have azide. Now, we do not have a second component now. It is just a vinyl azide. Now, in this case 1, 2, 3, 4, 5. So, you have all the carbons and nitrogen. What you will find if you use dirhodium carboxylate, in this case the carboxylic acid is a heptafluoropropionate, and normally it is I think dirhodium, it has to be 4, and with a catalytic amount of zinc iodide. What do you expect? You expect here and once again a pyrrole, and many of you can guess what is the mechanism, right. Let us say we put R2 here. So, it is R1 on this side, R2 here on this side. So, what is the mechanism? Again nitrene. So, many of you probably know that rhodium is let us say if you want to do produce carbene from a diazo compound, what is the catalyst you use often? Copper, right. even copper zinc couple, even copper sulphate also sometimes works. So, it is pretty easy. So, for to produce nitrine also very, similarly also the dirodium acetate acetate is a very useful catalyst to produce carbene from the diazo compounds Okay. And in this case it is basically producing the nitrine. So, once you have this nitrine, then I think all of us can write. I have not worked it out, but I think if you have nitrine. So, what you will find here, nitrogen double bond and and the ester here. So, it is again azirine right, and what next? What next? Okay. I think those who will be specializing in organic chemistry, I think they must read one reaction. This is a very fascinating reaction though, very fascinating reaction. This is known as vinyl cyclo pentene rearrangement. Again a thermal reaction, it is thermal reaction, vinyl cyclopentene rearrangement. What is it? It is nothing but, you see here, the starting metal is vinyl cyclopropane. If you heat it, I mean again just like in temperature, means 200-300 degree centigrade, just heat it. What you will find? You will find a cyclopentene. It is a very good reaction. I do not know why many people were interested at one point, but nowadays I do not see many examples in the literature, but very general reaction, very general reactions. You can accommodate all kinds of the substituents in both the substrates, I mean in the starting metal and the product. And if you look at what is this transformation basically, it is basically, although many of you know in the pericyclic reaction 1,3 sigmatropic rearrangement is not allowed, right. I should not say not allowed, it is not favored, that will be bad. But what you see here, it is a formal 1,3 shifting, normally 1,3 shifting, which is often seen in photochemistry. Okay. So, if you just basically shift this sigma bond to here, 1,3 shift sigma bond. So, that is what I mean. So all these reactions now here. Now you see there are plenty of example in heterocyclic chemistry. Although carbocyclic it is only limited to this vinyl cyclopropane and cyclopentene rearrangement. In heterocyclic chemistry you will find plenty of examples where you will find 1,3 sigmatropic shift. And in this case, I mean you see here this bond comes here, migrates, right. So that means this end breaks, migrates here, and to compensate this charge, and this double bond moves, that is it. So, what you will find, that means this is ester here, nitrogen. Now, if you bend this, so this should be R2 and now this is R1. Now, you know once it is formed this way, then of course, there are ways to isomerization to corresponding product. Okay. So, we are running out of time, let us look at one more very quickly. So, you can say this is considered to be the ring expansion now, right. So, vinyl cyclo, so ring expansion. Next example I will show you something quite interesting. This is I would name, although it was discovered by somebody else, it should be named as ring Boger's ring contraction. What is it? See, if you have pyridazine like means 1,2 nitrogen, and then ester group here, ester group on the other side, and then methoxy in one step. It is a very beautiful reaction though. We have been trying to do it, so far we have not reached the point. What you will see, So, you will get in one step. Is not it very interesting? How do you get it? See, one nitrogen is coming out. So, that means you have to choose a reagent, and one nitrogen means it has to be ammonia. So, if it has to be ammonia, then you have to supply hydrogen. So, how do you get the hydrogen? In this case, the reagent is almost always zinc acetate, zinc acetic acid, sorry, zinc acetic acid. So, mechanistically there are many possible mechanisms, but it is now agreed by most organic chemists that it gives first a dihydro compound where hydrogens are added across this pyridine nucleus in 1,4 fashion. Then rest this up to this first everybody agrees, but rest there are so many different possibilities. Okay, nitrogen can break and this thing that thing, but what Bogart suggested that this the bottom portion, this one is an imine. So, it will undergo hydrolysis, and then you have the rest of the thing here NH, and then you have NH2, and this is OMe, right, OMe. So, basically you get the hydrazine kind of thing, What next? I think all of you guess now. Once it opens, it was a 6-membered ring. In the beginning of the class I said the formation of 5-membered ring is very facile. So, obviously then it will undergo condensation with carbonyl group, and rest. So, you will get an aminopyrrole now. So, aminopyrrole OH, and this is the ester part here, this is again ester part, and then you have a methoxy here, right. And I think some mistake somewhere so far. OH, right. So, let us say then probably okay. I think eventually it has to reduce this. I think they suggested that it has to be methoxy here, then ester, methyl ester, and this methoxy, and then obviously then it has to undergo nitrogen cleavage, one more nitrogen cleavage to corresponding this pyrrole ring systems. Obviously, all of us know that nitrogen bonds are pretty weak bond compared to carbon bonds. So, this is a possibility. Okay. And what else? So, I think we have talked about ring expansion, ring contraction, and we missed one important point today, that is basically initially we talked about that alkyne precursor. If you go to the literature nowadays, you will find in many cases the alkynes are being used, and because they are readily obtainable, and it can display variety, or alkynes can display varieties of reactions. One of these reactions I will just this is the last example today. If you take this azuridine here, and then you take an alkyne bond, nitrogen, and this is benzyl R. So, what you will find in one step one can produce this is benzyl here, and this is R. You can produce R. You can produce this pyrrole ring system. What is the mechanism? Okay, in this case, how do you do it? One can think about thermally, because if you look at it is formally a 1,3 sigmatrophic shift, but in this particular example, platinum chloride has been used, platinum chloride, and around temperature at 100 degree centigrade. Many of you know, I mean this is well known, this noble metal can activate the triple bonds. So, either gold solubilized gold catalyst, platinum compounds, and this is because platinum. So, you have to use water and dioxin, which is a highly polar solvent to make this reaction go. But once again mechanistically it is basically the platinum coordinates to the triple bond. So, it gives the double bond character, and then all these migrations takes place. Okay. Migration takes place, but formally it is one can think about just as if it is a 1,3 sigmatropic shift, 1,3 sigmatropic shift. So, likewise there are many examples actually. Likewise there are many examples. There are other kinds also. There are, I mean, one can think about let us say an alkyne, and then let us say NH tosylate, and then ester here, let us say phenyl. Now, how can you make a pyrrole unit? Let us say again you see here from slowly to slowly, I mean ketone compounds, vinyl azides. Now, we are talking about the alkynes. Okay. Alkynes could be good substrates for pyrrole precursors, pyrrole products. And how do you, this is tosylate, sorry, this is tosylate. How can you cyclize? One of these ways to activate is that this noble metal like platinum, gold, mercury, silver, all these things actually all of us know activates the triple bond. But there are also in non-metal which can activate the triple bond. What is it? Iodine. Iodine. You must have heard of the term iodolactonization. If you have olefin and a remote carboxylic acid, right? You haven't. How come you don't talk to your lab mates? You should. So many actively works on iodocyclizations, iodolactonizations. Okay. I think Samim's work is based on that. So, if you do in this example, let us say just iodine, potassium carbonate and potassium carbonate and acetonitrile, you just in one shot you will get this iodolactone done. Corresponding iodine activates, this is tosylate and this. Then obviously, I mean you have a living group, and if you just add DBU and that at room temperature, it does two things. It creates a new double bond, isomerizes the double bond, and tosyl is also removed. So, I mean it serves three purposes. Okay. But main thing about this example is to see that cyclizations and your starting material. So, today basically we concentrated on the nature of the starting materials. So, 4 unit starting materials, 3 unit starting material, and in most of the other reactions are obviously 2 and 1, and so substrates varies from these aminoketones, diketones, all these things. Vinyl azides is a very good source of pyrrole unit, and now we are seeing this aziridine also could be, and then pyridazines. Pyridazines means that the substrate used for the radical, and then there are so many actually, there are so many methods based on alkynes. I mean if you are interested, I can show you the printout I have. I mean there is a like say more than, I think I counted here, this is a printout taken from its organic portal. It keeps on giving only pyrrole. There are about more than 60 different methods. Okay. So, but mechanistically and ideally they center on only few things. Okay, either Polnor or not. For example, you can arguably say Polnor, okay, the one that we talked about is nothing but is a Polnor extension. Why? Because all of us know acetylene can be converted to corresponding keto compounds. How? That mercury sulfate and this thing, that thing. So, that means when you are using an alkyne, it is essentially a carbonyl precursor. So, like that you can go on doing thing, that thing.